Hey there, everybody. Welcome back. We're going to do some examples with the conservative vector field. We want to show that the function, the vector function with y squared z cubed in the x component, 2xy z cubed in the y component, and 3xy squared z squared in the k component. We want to show that's a conservative vector field, and we're going to find the potential function phi related to it. So I've got the curl of f on the screen. You can see if you work it out, you're going to get 0, 0, and 0 for the I, j, and k components. So the curl of f, which is the curl of the gradient of phi, equals 0. So we want to find phi. We're going to go off gradient of phi. What is gradient of phi? Do I write it down below? No, I don't. Remember, it's d phi dx, d phi dy, d phi dz. So if this vector here is related to that, we can correlate d phi dx to that, the I component, d phi dy to the j component, and d phi dz to the k component. So d phi dx means it's the partial derivative with respect to x. Let's integrate it with respect to x. So take time to follow this, because this blows up a lot of students. When we integrate a function, we don't have limits in integration, we have a constant that gets attached to it. Normally we just write plus c. We normally just write plus c when we do an integral. But when we're doing partial derivatives, it may not just be a constant. It may be a constant function with respect to the variable. So if I integrate this with respect to x, it just becomes xy squared plus z cubed, but we haven't addressed y and z. Any function of y and z, like let's say we had plus y squared z, let's say we had that. This was xy squared plus y squared z. When I do d dx, a partial derivative with respect to x of this, I'm missing something. I need a z cubed there. I'm going to get y squared z cubed plus 0, because this does not have a x in it. It goes to 0. So when we integrate, we have to say it's a constant function with respect to x. So a function of y and z, which still may be a constant value. It may not have y's or z's in it, but that's what we got to do. Okay? Let's work off of that. So this is my phi function as it is. I integrate it with respect to x, and I'm attaching some constant function. I don't know what it is. I do know what the partial derivative is with respect to y, though. It's listed right up here. So I'm going to take the derivative of this with respect to y, and I'm going to match it up to this. Okay? So if I take the derivative of that with respect to y, I've got to bring down the 2. I've got 2xy z cubed, plus I've got the partial derivative of g with respect to y, and that's going to equal d phi dy, but I've got d phi dy listed up here, so I'm bringing that down right here. That's coming down right here. And now I'm going to solve for the partial derivative of g. If I subtract 2xy z cubed from both sides, I get the partial derivative of g with respect to y is 0, which means it is not a function of y. When we integrate a function that has 0, we normally get a constant. But when we integrate this, the constant, it might still have a z in it. It might have just been z squared. And so the derivative with respect to y goes to 0. So we're going to say g of yz is actually just h of z, which is a constant with respect to y. Just like we did up here, we had g of yz. Now we have h of z. So where do we stand? Let's go back and rewrite phi with our current information. I got phi is xy squared plus z cubed. It turned out g was just a function of z. So I'm going to take the derivative of this with respect to z, And I'm going to pair it up with what we have up here with d phi dz. And then we can find out what h of z is. Okay, so this is a three-step process. I take the derivative of it. We bring the 3 down. I've got 3xy squared z squared. Plus, now I can just do a regular derivative, h prime of z, because it's only one function or one variable. That should equal the d phi dz we have up here, which is 3xy squared z squared. So again, I solve for h prime of z. I get 0, which means when I integrate it, h of z is just a constant, and this is a real constant. No variables in it. And so our potential function, phi of xyz, was just xy squared z cubed plus some constant of integration. Okay, so that's the big takeaway. When you are doing your integrating to find the potential vector or the potential fields, the potential functions, when you integrate and you get the constant of integration, it still may not just be a constant. It may be a function of the other variables. So you got to take this a little bit slower. Peace.